It's May 9th, 1973, in the Crimean city of Simferopol. Alexander Basilevsky and his co-workers are sitting in a secret base. They are staring at an array of instruments. Instruments that they use to control a robot. It's a tricky job, as all they can see are grainy images on a small CRT that only updates every couple of seconds. But what makes this task even more stressful is that the robot they are controlling isn't even on the same celestial body as them. It's on the surface of the moon, and they just crashed it into a crater. The spacecraft they are controlling was called Lunochod 2, which roughly translates to Moonwalker. And this happening isn't actually all that surprising, given that they only had a small CRT display, and the camera that fed that monitor was blinded by the sun during certain times of the lunar day. And worse still, the entire team was overworked and tired. However, the damage was already done. They had touched the crater wall, and by accidentally using the solar panel array, which was somewhat shaped like a spoon, to scoop up regolith, they covered their primary energy source in dust. They immediately noticed a loss of power, but the rover remained operational, allowing them to drive out of the crater. But that moment of relief was short-lived, as the fast approaching lunar night required them to close up the vehicle. They were forced to dump all that dust onto their instruments, resulting in the spacecraft overheating during the next lunar day, ending the mission. Despite this incident and the resulting mission failure, the Soviet moon rovers were a huge success. So successful that Lunochod 2 would have gotten a successor, Lunochod 3, but unfortunately this one was never launched. If you want to learn more about this fascinating period of Cold War space history, I highly recommend this article by Andrew Chalkin, on which this introduction is based. The link is in the description. But this incident also highlighted one fundamental limitation of remote-controlled vehicles on other celestial bodies, that is, delay. Communicating at basically light speed might be fast enough for Earth, and while a 3-second round-trip delay to the moon might be somewhat manageable, a 4 to 24-minute delay to Mars will definitely be a problem. Considering all this makes them driving 39 kilometers on the surface of a different body in space even more impressive. This was a new record, and this one stood for multiple decades and was only surpassed by NASA's Opportunity rover over 30 years later. But NASA breaking this record was only possible with massive improvements in computing that made autonomous driving a viable solution. In this video we will explore how NASA's Mer Missions, that Opportunity was a part of, autonomously navigated the surface of Mars, and in the end also take a quick look at a very similar approach by the European space agencies. But what even were the Mer Missions? The Mer Missions consisted of two twin rovers called Spirit and Opportunity that were launched to Mars in 2003 on top of two Delta II rockets. Their missions were initially planned to last only 90 Martian days, but both greatly surpassed that goal, with Spirit lasting until 2010 and Opportunity continuing until 2019. Primarily, they conducted geological studies on Mars, analyzing rock mineral compositions to find evidence of water, as well as taking beautiful images of the Martian surface. But that's not the focus of this video. If you want to learn more about the fascinating science they conducted, I recommend this video by Astrom, which covers the entire lifespan of Opportunity. Link again in the description. However, what is this video's focus is autonomous navigation, and they both demonstrated autonomous driving capabilities on the Martian surface. But let's step away from specific missions for now, and begin by imagining ourselves waking up in an unfamiliar world that we want to explore. The first thing we would do is look around to learn about the environment, and by doing this we create a representation of the real world in our minds that we can use to identify potential risks, interesting places, stuff like that. In general, we use this map as the basis for planning what to do next, and our rover is in the same situation. We assume it just landed on some space object and now needs to learn about its surroundings. In order to familiarize ourselves with the environment, we want to translate the real world into a map that a computer can understand. Let's look at one way of doing this using this example. We have the area right here and then measure at a bunch of points. If we now take a look at the values of the individual data point and instead of imagining them in a 3D environment, put them into a grid, we get a digital elevation model, or short DEM. So for each of our data points, there's now a height value in a grid. Of course, in the real world, you can't just simply deform a grid like I did here to illustrate the principle. Instead, you use measured values to calculate the elevation of each cell. We can also improve the accuracy of our map by increasing the number of cells, assuming we have accurate enough measurements. But this will also increase the computational complexity. So as always in computer science, you need to find a good compromise for your specific application. In the next step, we can also extend the DEM with some extra information, like a texture map, mesh information, a thematic map, or other things to get a digital terrain model, or short DTM. An autonomous rover also has to create a map like this as a basis for obstacle avoidance and navigation. For this, we need a way of measuring the environment, and there are quite a few, like LiDAR, sonar, and other sensor types. But there's also stereoscopic vision, which is a technique very similar to the way humans see in 3D, and also NASA's technology of choice for the Mer rovers. Similar to our eyes, stereoscopic vision uses two cameras mounted next to each other. Both cameras take an image at the same time, and these images are very similar, but not identical, as they are taken from slightly different perspectives due to their mounting offsets. By now looking at the difference between these two images, we can obtain some information about depth. Objects closer to the camera have a greater offset in the two stereoscopic images, while objects further away shift less. And by using additional information about the cameras, like the lens's focal length and the distances between them, we can not only measure distances relative to each other, but also estimate actual distances from the camera array to objects. Using many of these measurements, we can create a cloud of individual measurements in 3D space, also called a point cloud, which can be used to estimate a DEM, or even create a 3D representation of objects. But this process is also pretty sensitive. The cameras need to be as close to identical as possible. Different focal lengths, alignment issues, or dirt will make accurate measurements difficult or even impossible to achieve. Also, objects visible in only one of the cameras or parts of the rover itself need to be discarded. As already shown in the animations, the Mer rovers also use stereoscopic vision with their two LAAS cams. But not only to create the aforementioned point cloud and DEM, but also to generate a thematic map, in this case a traversability map. A traversability map is a rectangular occupancy grid of XY cells, like the DEM, but instead of containing height information, each cell is assigned a traversability score. This score is an estimation of whether the rover could traverse a given cell in the real world, with a value of 1 representing a traversable cell and a value of 0 representing an untraversable cell. Values between 0 and 1 are also possible to indicate a cell that's somewhat traversable, and sometimes a star or just the value 0.5 to indicate an unknown cell. In practice, the rovers created a 10 by 10 meter grid with themselves at the center. This grid was subdivided into cells measuring 20 by 20 centimeters, and that corresponds to the size of one rover wheel. Each cell got initialized with a value of 0.5, and all cells visible within the 115 degrees field of view of the HASCAMs are analyzed for traversability. During this process, the rover uses its stereoscopic camera array to create a DEM of the area in front of it. Then an imaginary rover-sized object is virtually placed in the center of the cell being analyzed. With our virtual rover being bigger than this cell, that is again just the size of one wheel, we can now use the surroundings of this virtual environment to check for all kinds of obstacles. Using this process, every cell is checked for step, surface roughness, and steep angles. And if our imaginary rover does not encounter any of these problems, we mark the cell as traversable, or here green, and if it does, we mark it as red. Additionally, there can be yellow and orange cells to indicate varying levels of traversability. In the next step, we expand all obstacles by the rover's radius, to ensure that the rover always stays safely away from dangerous areas. Our rover now has a decent understanding of the terrain around it. However, for autonomous driving, it also needs to plan its movement and trajectory. For this, it also needs to receive a goal that it's supposed to drive to, usually from mission control. And now we can use our favorite pathfinding algorithm to determine the best route. In later versions of the flight software, the D-star algorithm was successfully demonstrated on opportunity to choose a suitable trajectory. However, most of the time the rovers used a probabilistic model to generate a set of circular trajectory arcs. These arcs are then evaluated for safety and how close they bring the rover to the previously set goal, and the arc that best meets these two criteria is then selected. After that, the rover drives 30 centimeters along the selected trajectory, then it stops and repeats the entire process. In the next iterations, the traversability map is updated and expanded with new data, allowing the rover to gain an understanding of the terrain beyond the camera's field of view. We can even make use of the point cloud again here for the driving process. Although the rover drives what it thinks to be 30 centimeters, this distance might be somewhat inaccurate, and by recognizing the same landmarks before and after driving, we can triangulate the rover's position again, to compensate for things like wheel slippage on steep slopes. This technique is called visual odometry, and it made it possible for the two Mir rovers to drive on slopes of up to 30 degrees instead of just 15 without it. This cycle of driving, stopping and driving again continues until the rover either reaches the goal or gets stuck in a situation from which it can't get out by itself, at which point it awaits further commands from the team on Earth. The Mir rovers were capable of performing all the processing for one of these steps in about a minute, even with their very limited resources. And by processing the data on the rover instead of transmitting it, the amount of data sent to Earth could be reduced by an estimated 20 to 100 times, freeing up precious bandwidth for scientific data and significantly speeding up the travel process. So, that was a lot of steps. Let's do a quick recap of the entire process. The rover is stranded in a completely unknown environment. Then it uses its stereoscopic camera array to create a point cloud of the terrain. This point cloud is then used to create a digital elevation map. The digital elevation map is used to evaluate the traversability of cells in a traversability map. Potential trajectory arcs are superimposed onto the traversability map. The best trajectory arc is selected and the rover drives 30 centimeters into that direction. And the entire process is repeated until the rover has either reached the goal or gets stuck. Of course, there's also an acronym for the process, and that is GESTALT, which stands for Grid-Based Estimation of Surface Traversability Applied to Local Terrain. This approach suited NASA well for the Mer missions, but it struggled with complex hazards and long navigations. Mer's approach to navigation mostly reacts to obstacles as they occur, rather than planning a long route in advance. The rover stops every 30 seconds and basically discards the old route and plans a completely new one. This can lead to it choosing paths that are good in the short term but potentially bad in the long term. That's why European space agencies introduced a more deliberate approach, aiming to plan further into the future to make a highly autonomous mission navigation system possible. The two navigation systems share a number of similarities. Both use stereoscopic imaging cameras to create a DEM, and both systems operate while the rover is stationary. So both drive a short distance, hold, and then analyze their surroundings. Both approaches also implement a traversability map. But this is also a key difference. While the Mer DEM and traversability map had a resolution of 20 by 20 centimeters, the CNES map had a resolution as fine as 5 by 5 centimeters. Cell difficulty evaluation is also done differently. Instead of placing a rover-sized object on the cell and checking for slope, step, and roughness, a virtual rover axle is placed on the cell and checked for step and slope. If any of the axle orientations exceed a maximum tilt angle, the cell is classified as untraversable. Another major difference is the look-ahead distance. Mer selects an arc that might span a considerable distance, but in reality the rover only drives 30 centimeters along that arc before selecting a new one. Therefore, the effective distance the rover plans ahead at any given moment is only 30 centimeters. The CNES approach, on the other hand, can plan up to 20 meters ahead, depending on the height the camera array is mounted, and of course being limited by objects blocking the view. Furthermore, it uses closer sub-goals in already mapped regions instead of a single distant goal. These sub-goals are positioned at the boundaries of known and unknown regions of the map within a traversable cell. Another key difference from Mer is how possible trajectories are generated and selected. As mentioned earlier, the D-star algorithm was successfully demonstrated on Curiosity for finding an optimal route, but most of the time they relied on a probabilistic model. CNES uses a two-tiered graph search algorithm system, where the A algorithm determines a broad path from the current position to the subgoals, and the A-star algorithm then finds the optimal path to the next subgoal. A and A-star are also pathfinding algorithms that I won't go into detail about in this video, but I placed links to great explanations in the descriptions. In general, the approach by CNES and LAAS is an improved form of the process demonstrated by NASA during the Mer program, and it is also one of the major contenders to be used on the Exomars rover by the European Space Agency, which are used in the 3D animations of this part of the video. The mission was originally supposed to be launched in 2022, but due to the Russian invasion of Ukraine, ESA ended its partnership with Roscosmos, delaying the mission. It's now expected to launch in 2028. In the end, every challenge faced by these early missions paved the way for today's advances in autonomous navigation, and it's incredible to see how far they come. Thanks for sticking around to the end, and if you're curious about more space missions, don't forget to check out the links in the description.